Okay, we're going to talk about the pH scale, which is section 7.5 in your book. This is all about the power of hydrogen. Okay, pH means how we express acidity or basicity in terms of concentration of the hydronium ion. So as a reminder, hydronium ion, we get this from the Bronsted-Lowry. So remember how we had an acid, such as HCl. If we show water in the equation, the hydrogen will donate to the water, and we get hydronium and then the anion. Now, another thing we can also use instead of hydronium is the hydrogen ion. And this one comes from Arrhenius' theory. So, if we go and show hydrochloric acid, instead of showing water, we just show AQ, it will break apart into hydrogen ions and chloride ions. So whenever we see hydronium, hydrogen ion is also an acceptable ion to exchange. And whenever we see brackets, brackets always mean molarity, which is the main unit of concentration. Okay, so here's a chart below, and this is talking about our pH, our hydrogen ion, or we can say hydronium ion, or we can say acid, along with a hydroxide and a POH. And we'll talk about hydroxide and POH a little bit later. But notice what's happening. If we have a pH of 14, our hydrogen ion concentration is 1 times 10 to the negative 14th. So the pH is just the exponent, but it's positive. And if you notice, this happens all the way down. So a pH of 10 has a concentration of 10 to the negative 10th. A pH of 5 has a hydrogen ion concentration of a negative 5, 1 times 10 to the negative 5th. And then you can also notice here that your hydrogen ions is inversely proportional to your hydroxide. So here, our hydrogen is increasing as we go down, and our hydroxide increases as we go up. So they are inversely proportional. Another thing to notice here is that our numbers on the hydrogen ion concentration and the hydroxide always add up to a negative 14. So here's our negative 7, that equals negative 14. Negative 3, negative 11 equals a negative 14. They always equal up to a negative 14, which is why the pH scale is based on a 0 up to a 14 because of water. Water right here, okay, pure water has a pH of 7, and so we have 1 times 10 to negative 7th hydrogen ions in water and 1 times 10 to negative 7th hydroxide ions in water. And then from there, everything gets broken up. Okay, so that's kind of just a little thing for you to kind of look at in terms of acidity and basicity. Okay. Again, we've already mentioned this, but as the solution becomes more basic, the hydrogen ion will decrease and the hydroxide increases, and the opposite is true for an acid. As a solution becomes more acidic, the hydrogen will increase and the hydroxide will decrease. Okay, now the cool thing about acids is that they're based on logarithms. And I know logarithms aren't everybody's favorite, but we're just doing very simplistic logs in acid base. So a log just means that it's equal to 10. It has powers of 10. And every 10 has 1 pH unit. So, for example, let's say that we have a body of water, and the pH of the body of water is 6. Near this body of water, we have a factory. And the factory cleans everything with the water, and it has the water that comes out of the factory of a 4. So if I was to say, what's the difference in my hydrogen ions between this two, we're going to look at the pH numbers. Sorry, this is the pH of the factory water and the pH of the stream. So the difference here between these two units is 2, correct? 6 and 4. The difference is 2. So we'd say 10 raised to the second. And that would mean that the factory has 100 times more hydrogen ions as far as concentration than the pH of 6 in the stream nearby. So that's what we're talking about when we're talking about the power of 10. If, let's say that we had a difference of, let's say that our pH of our water or our stream nearby was a 7, the difference here would be 3, which means that it would be 10 to the third, which is 100 times more hydrogen ion concentration. Okay, on the pH scale that we're going to look at, okay, 7 is your neutral, 0 is right there, and here's 14. So from 0 to 7, we're dealing with an acidic concentration, and anything above 7 is basic, and then 7, of course, is neutral. Now, there are fine lines in between here, but for this class, we'll just say 7 is neutral, anything below 7 is acidic, anything above 7 is basic. Okay, and the equation to find a pH is down here. pH equals the negative log of hydronium, and there's some interchangeable things here. So remember, we talked about this last slide. We can say hydrogen is interchangeable, hydrogen concentration, hydrogen ion concentration, or any acid. So whenever we have either hydronium, hydrogen ion, or an acid in an equation or in a question, we can use this equation, this negative log hydronium, to find the pH. So let's do some problems. Okay, determine the pH of a 1 times 10 to the negative third molar HCl solution. So first thing you need to do is you need to look at the substance they're giving you. They're giving you HCl. And you need to ask yourself, is this an acid or is this a base? And this is an acid because we have a hydrogen and it's bonded to a nonmetal, which is the chlorine. So because of this, we can put it into our pH equation. pH equals the negative log of hydronium. And remember, this can either be a hydrogen ion or it can be an acid. And since HCl is an acid, we can go ahead and we can plug that in. So when we plug this in, all we're going to do is pH equals the negative log, and then in parentheses, you're going to put 1 times 10 raised to the negative third in your calculator. And when you do this, your pH ends up being a 3. And that's your answer. And there's no units for pH, so it's just 3. Now, if you remember from our first slide, remember that if we have a 1 times 10, whatever this exponent is, always equals just that positive number for the pH. So if we said 1 times 10 to the negative fifth, it's going to be a pH of 5. So that's another way you can look at these as well. Okay, let's look at the second one. What is the pH of a solution if the hydronium ion concentration is 6.7 times 10 to the negative fourth? Okay, so let's look at what we have. It's talking about, it's giving us the hydronium ion concentration. Well, we know that matches what we need for our pH, so we can go ahead and just plug this in. So pH is going to equal negative sign, log, and then you're going to put in 6.7 times 10 raised to the negative fourth. And that is going to equal 3.17. So the pH here is 3.17. Whenever you have numbers like this one, 6.7, or anything that's not a 1, you have to put it into your negative log. You can't just solve for it up here like you did before. Okay, let's look at some other problems. Okay, another thing we can look at is a hydrogen ion concentration from a pH. So how do we find hydrogen ion if we're given a pH? So if you take that last equation for pH and you manipulate it, you would get this as your equation. Hydronium ion, which of course, remember, this can be hydrogen ion or it can be an acid as well. is going to equal 10 raised to a negative pH. That's all you have to do. So let's look at the first question. What is the concentration of a HNO3 solution that has a pH of 4? So first of all, HNO3, is this an acid or a base? It's an acid, and remember the acid always correlates to a pH. Okay, so, and here's our pH of 4. So all we're going to go is 10 raised to negative 4 equals 1 times 10 to the negative 4th. And concentration, remember, is always molarity. That's our unit. Molarity is moles over liters. Hopefully you remember that from our last chapter. So that's our concentration if we have a pH of 4. Let's do the next question. What is the concentration of a HCl solution that has a pH of 5.74? So again, look at things. HCl, this is an acid, so this correlates up here to this acid. So all we have to do is go 10 raised to negative 5.74, and that's going to give us a concentration of 1.82 times 10 to the negative 6th molarity, and that would be our answer. Okay, so again, this is finding a hydrogen ion concentration, so the molarity, if we are given a pH. Okay. Now, the next thing we're going to talk about is hydroxide ion concentration. So with this one, you have to remember that hydroxide is OH with a negative charge, and we're dealing with a base. Okay. So on this one, you're looking for anything that's an base, or if it talks about a hydroxide, an OH negative. Okay, now there's 3 equations we're going to look at. This first one is POH. This stands for the power of hydroxide, and it just equals the negative log of hydroxide. And another thing you can use here again, like I mentioned before, is a base. So if they give you an OH or a base. Okay, another thing that's helpful is the second equation. The second equation is when we need to go from a pH or a POH. So this just means that the pH, the power of hydrogen, plus POH, the power of hydroxide, is equal to 14, and we're getting that 14 because of the pH scale. Okay, and then the last equation is going to be hydroxide ion concentration. We can also have this as a base, is going to equal 10 raised to the negative POH. So you notice that the first and the third equations here are just like the acid. We're only exchanging them for things with a base. Okay, so let's look at the first problem. The first problem says 0.001 molar NaOH has a pH of question mark. So the first thing we have to do is look at the NaOH, and you have to ask yourself, is this an acid or is this a base? This is a base because it has a hydroxide. So it wants to know the pH, but pH is associated with an acid. So what we need to do here is we need to find the POH first. So the first thing we're going to do, number 1, I'm going to put this up here, is we're going to find the POH. Okay? And we can do that because of this first equation. So if you look at all of your equations and you look for POH, okay, we want to find it, and the only equation that we can find it is this first one. So we're going to go ahead and do the negative log of our 0.001, and that's going to give us our POH. So our POH is going to equal a 3. Okay, and that's because of what we're given here. We're given a concentration. So if we look at all 3 of these conversions, which is the only one that uses a concentration, well, that's our first one. Okay, now from here, we're going to use the magic of this second equation. We're going to go from a POH to a pH. So right here, what we're going to do is we're going to say pH plus POH equals 14. And since we have the POH, we're going to plug that in. So pH plus 3, and that's coming from here, equals 14. And now it just becomes an algebraic equation. I'm just going to subtract 3 from both sides. That cancels. Our pH equals 11. And this should make sense because on our periodic table,